Okay, we're looking at invert binary tree today. This is our first problem in the tree section. Yeah, it's gonna be fun. It starts out just like linked lists with a few easy problems just to kind of get our gears going with the concept. And then these actually get pretty like complex and pretty fun. So just as a note here, because it won't come up till later, but this might be something that you're thinking about. If you've learned about trees a little bit before, these are not necessarily binary search trees. So binary search trees have the additional trait that for any node in this tree, the left is smaller and the right is bigger. That is not the case for trees in general. So there's no like requirement there. It's not super relevant today, but just FYI, there are binary trees, which just mean each node has up to 2 children. And then there are binary search trees that have that added trait. So just a little disclaimer out front. All right, let's take a look at the problem though. So it says you are given the root of a binary tree and we're calling it root. Okay, and we want to invert the binary tree and then return its root. Great. Yeah, so if we take a look at this example, it's a little bit, we'll zoom in a little bit here. We've got this binary tree here. When we start, so just like with linked lists, like they give us all of the numbers in the tree and it's listed kind of in a like level order. So it's like the top node and then the next layer of nodes and then the next layer of nodes. We're not literally going to be given this list right here. This is just a representation for us to understand what's in the tree because they don't want to make a diagram for every single one of these, right? Okay, anyways, the point here is that if this is the tree that we start with, you can see in the result, its children have been swapped. So its original left is now its right, and its original right is now its left. But this is also the case for all of the descendants. So for example, this node right here originally had 6, 7. Anyways, but after we invert it, it's going to have 7, 6. Similarly, this guy originally had 4, 5, and instead when we invert it, it has 5, 4, right? So we need to not only invert the children, the immediate children of the root, but also all of their children need to have their children reversed, and so on and so forth for all of the nodes in the tree. And obviously, well, hopefully it's somewhat obvious, for a node that is already at the bottom, which is called a leaf node, it doesn't really matter what happens to its children because it has a none and a none, right? So if we swap those, it still has no children. So yeah, which is kind of an important idea, actually. We'll talk about it in a sec. Great, so just a few more examples here. This one, pretty straightforward. It's got 3 as its root, and originally 2 as its left node, and 1 as its right node, and we're just going to swap those, so it has 1 as its left node, and 2 as its right node. Oh my gosh, an alumnus is here. Welcome. Anyways, so yeah. Hopefully pretty logically sound here, or logically intuitive. The one like edge case that they give us here is that if we have no tree, basically, so root, you can see root here is an empty list. If we're given, in the case of Python, none, then we can just return none. Okay, speaking of which, one of the constraints they give us is that the number of nodes in the tree will be between 0 and 100. So it's possible there's no nodes. It's also possible there's up to 100 nodes. And the values, which we don't care about a ton, we're not going to manipulate those, are between -100 and +100. All right, so we'll diagram this a little bit. We'll also talk a little bit about traversals, and then we'll get to the code, which is pretty short today. So let's say we've got this tree here. I'm just going to make it have whatever numbers. Oh, and I should say, similar to linked lists, the way this is structured in the code is that any particular node, the only things you'll know about the list, at least when we start, are what is the root, right? So we're given the root, we'll know what is its value, what is on its left pointer, and what is on its right pointer. So that's all we know to start with. We don't actually, I'm covering it with my hand, but I'm realizing you guys aren't here. We can't actually see these guys, right? They're kind of obscured when we begin. And so we need some way to programmatically travel the tree and also reverse the children as we go. Okay, So in terms of like this somewhat simple example, if it's just a node and it's got two descendants right here, so this is like the overall situation we're considering because we have to do this for every single node. What we want to do is just a simple swap, which we can do something like this. We can say like, let's temporarily store the left node. And then we can say, hey, let's go ahead and make, not right, but root.left. Let's make that actually point at the right node. And then we can make root.right point at the left node, and we can't say root.left, right, because we actually changed it a second ago. Instead, we stored it in temp. We're going to make it point at temp, right? So this is basically the algorithm that we can talk about for swapping or inverting one node. Okay. Now, if we had more than this, so this is obviously a somewhat simple example, but it would work for this simple tree. Now, we need to be able to extend this to any size of tree, right? So I'll just add on some nodes here. Maybe we have a 4. Well, here's what we'll do. We'll have a 4 and a 5 here, and I'll have just a 6 on this one. Okay. Now, we have a few options as far as how we can get through this tree, but since we need to travel the entire tree, and we also need to do something to each node, let's talk a little bit about like the order in which we do this. There's 3 terms that we're going to use in some following tree problems. We have pre-order, in-order, and post-order. And these are options for how we traverse the tree. So as we go through the tree, we want to do something to each of the nodes, but the question is, do we do it to the children first and then the node that we're actually on? Do we do it to the node we're on and then the children? Maybe we do the left child and then the node we're on and then the right child, right? And so each of these is captured by a different term here. Pre-order means we do the self, and then technically it doesn't have to be left and then right, but basically you handle yourself and then you handle your children. Okay. In order is when we handle the left child and then the self and then the right. And post order is when we handle the 2 children first and then the self. Okay, so basically the order in which we handle the self node is going to determine if it's pre or in or post order. Okay, so between these options, basically what we're saying is like, do I reverse my own children and then handle their children? Do I reverse the left child and then handle myself and then reverse the right child? Or should I do the children first and then handle and then invert myself, right? The only one of these that doesn't work actually, so 2 of them do work, 1 of them doesn't work, is the in-order traversal here. Okay, and the reason for this is, so let's just go ahead and carry it out for a second here. If I were to swap the stuff in the left tree, right? So we're going to kind of take for granted how exactly this happens just for a second to talk about the order here. So swap your children. Originally it was 4, 5, now it's 5, 4. Okay. And then we invert the self. So now if we make these switch places, okay, so if we do that and then we invert the self and now we handle the right child, well, here's the problem. The right child is what the left child was before, right? So if we decide to do this in order, where we handle the left child and then invert the self and then invert the right, the problem is we'll actually end up swapping this back to what it was before and not handling the new left child at all, right? So this is a problem for us. It doesn't actually invert the tree. So we need some way of making sure that we actually handle both of the children, right? And so like I mentioned earlier, it turns out both of the other options, pre-order and post-order, will actually do that for us. If we decide to invert immediately, So again, that just means swap where my left and my right child are. This is totally fine because although we're calling them different names than we were before, we can still go into both of these trees and do our inversion, and everything works out the way that we want it to. Alternatively, so let me go back to the original state of the tree. Alternatively, if we decide to reverse everything immediately, so you guys swap, and then you guys swap, that's totally fine too. Either option works, and the code is actually very similar. It's just the placement of where we put some of the code blocks will change. So yeah, so inversion for one single node, nothing too crazy. You just swap the left and the right. Now, what we'll do to make this happen for the entire tree is we'll do this recursively. And so what I mean by that is if you want to know how to swap or how to invert the entire tree, you just need to make sure that you invert the left tree, invert the right tree, and then swap those, right? And this is true as we go down the tree as well. So for the entire tree, that's true. Invert the left, invert the right, and then swap. Now, if we look at a subtree right here, the same thing is true. We can just say, hey, invert the left, invert the right, and then swap, right? And no matter how far this goes down, so I'll even continue the tree for just a second here. Maybe this is a 7. Maybe this, let me think. It's a 9 or something like that. We can go layers deep into this. So for the overall tree, invert the left, invert the right, and then swap. And then for this subtree, for example, invert the left, invert the right, and then swap. Okay, and then now for this subtree, invert the left, invert the right, and then swap. And by the time we're done with this, I know it's looking quite scribbly right now, but by the time we're done with this, we'll have dug all the way to the depth, or all the way to the bottom of the tree. We'll know that everything on the way back up is already swapped. We'll do that all the way down the right tree, and by the time we get back to the top, we know everything's already swapped, and then we can just swap the left and the right. And so this is going to be a recursive solution. This whole idea of you can just reapply that same logic to every node is pretty much exactly what we're going to do. We're going to continue to call this swap function, and we'll talk about how to structure the code so that this actually works. I think it's easier almost to see the code and then figure it out from there. But again, the core idea here is that our goal should be invert the left tree, invert the right tree, and then swap the left and the right. Or alternatively, like we said, so we could do this pre-order, we could say swap the left and the right, and then invert the left tree and invert the right tree. That works just fine too. Okay, now, sorry, I keep saying let's go to the code. Let me say one last thing. I've sort of said that oh, well, surely it's easy to invert the tree, right? And that is kind of something that we are assuming we can do, right? Because we know that, we know how to invert a single node, and now we're just applying that to the whole tree. So when I'm saying invert the left, invert the right, what I'm saying is do the whole thing, but on the left subtree. Do the whole thing that we're talking about, but on the right subtree. Anyways, let's look at the code, because I think that's going to make it make more sense than just using words. Okay, so we're given the root node, right? If we want to invert the left subtree, all we have to do is say, self.invert tree, and instead of passing the root that we were given at the beginning, we can pass whatever's at the end of its left pointer. Okay, similarly, if we want to invert the right half of the tree, we just call this same function, assuming that there is some way to actually invert the left and the right. And then, once you know that your left subtree and your right subtree have been fully inverted, now all you have to do is swap them with each other, right? And how do you do that? Well, again, we have this swap code where we can say something like temp equals root.left, root.left equals root.right, and then root.right equals temp. Okay, so root.left has whatever was formerly at root.right, and root.right has whatever was formerly at root.left. And so this portion right here is just swap the left and right subtrees. Okay, and so again, the recursive solution is a little bit funky here because what we're trying to say is like, let's assume that there is some way to do it, right? And it turns out that the way to do it is to do the same thing. So for the next node down, we would say, hey, go ahead and invert your left and right subtrees, and then swap the left and right subtrees. And that's going to be the case for every single node. If we do this all the way down to the bottom, then the entire tree will be inverted, right? Now here's the problem. Well, a few problems actually. The question that we need to ask is like, when do we stop, right? When do we no longer need to invert things? And we actually have a few ways to detect that. We can either say, hey, if you don't have a left or a right child, you can stop. Like trying to invert your children is going to do nothing, right? So one option would be to say something like, if not root.left and not root.right. Okay. The other option, and this is kind of interesting here, is to just say, hey, when you get to the none node itself. So like when you go here and like you're sort of, like you've reached this point, we've passed in none. It's not really a node, it's just like, it's not a node, but we're passing that thing. We're passing whatever was at the end of that pointer, which is none in this case. So the alternative is just to say, if not root. And we've done a little bit of recursion, but just as a small review here, this is what we refer to as a base case. This means we don't need to recurse anymore. There's no further for us to go. We have found a stopping point where we have a definitive action that we should take instead of kind of a like an abstracted like do this again on the left node or the right node. We can say, actually, if we get to this situation, we know exactly what we should do. And what should we do? Return. Oh, actually, hold on. Let me think about this. It doesn't super matter what we return here, I guess. We could return root. Yeah, what we'll pass back up is not super of concern because at the very end we just want to. Ooh, is that right? Yeah, I guess we're gonna pass a bunch of things back and like never use them. Like I don't need to know what was passed back from the bottom tree because like I'm not gonna use it. Yeah, hate that, but that's okay. Okay, so let's figure out which one of these options we actually want to take here. If you reach this situation, would that cause any problems? No, not really. Oh, okay, well, hold on, let's think about this. If we had something with one child, well, okay, here's what I'll say. This definitely works. In fact, we can just return here. We don't even need to return the root. So this is basically just saying, like, once you get to the void at the bottom of the tree, there's nothing left for you to do. Don't worry about it. What I'm concerned about with this option right here, although I think there's probably a way to make it work, is if it has one child, and we don't, like, so if we have it structured like this, if it has one child, then we have nothing to capture the situation where, like, if it doesn't have a left child, we'll call this, and then we have nothing to capture the situation where it's none, right? So don't like that because it's going to give us runtime errors. So instead, we will go with this option because I also just happen to know that that works. And I think we can, like, I don't think everything has to return, like, we can just return here. Oh, you know what? I forgot that there is an edge case where there are no nodes at all. So if there's not a root at all, we can just return none. Great, that's probably what we want. And then in the other situations where we actually have a root at the top, we'll call this function, we'll get back something from it. We'll get back like whatever the root of that subtree is. We're not going to use it, and at the end we just return the node that we're working with. So this is going to guarantee that at the very top level from where we first called the function, we're going to get back the original root, but with its subtrees inverted. Okay, I'll be yapping. Let me run that. I probably messed something up. Let's find out. Okay, she worked. Let's submit, and then we'll just make one small swap to the code to show that there's some other stuff that works here too. Okay, so yeah, she works. Again, this is going to be what we call a post-order traversal, and this is because we handle the children before handling the self, right? And again, what's kind of cool about this is if we just do it the other way. So this is saying, hey, go ahead and swap my left and my right, and then go ahead and invert the left and the right. That's fine too. As long as we don't invert one, swap them, and then invert the other, we're going to be fine here. So just for demonstration, she works the other way too. Great. So this idea is definitely going to be common across tree problems. The idea of like if we can figure out how to handle this node and its immediate children, then we can apply that logic recursively to all of the descendants, right? And finally, the last piece of the puzzle is we need some way to capture when we've reached the end and we no longer need to recurse, which we call a base case. This is going to be like, I think most, if not all, tree problems will work out this way. So yeah, and that's that. Again, nothing too crazy to start off with here, but stick around for the next few tree problems because you'll need that knowledge for some of the tougher ones. But we'll call it for tonight, unless anybody has questions, which I would be happy to answer questions if anybody has questions. 4 sons. Boy is typing. Sweet. Glad it's making sense. And as always, if you have not tried this problem yourself, go give it a shot. Now that you've seen the solution, you don't really know it, or it's not going to be super useful to you unless you can do it yourself. So the way we have it configured right now, this is pre-order, which again means handle yourself first, right? Swap your left and right child, and then handle your children. That's pre-order. And the other way we had it, like this, is post-order. This says handle the children first and only handle yourself after. Yes, yeah, so definitely good comment there as far as like returning the full tree. So similar to linked lists where we just return the head and it's hooked up to the rest of the list, for trees, often what we'll do is we'll return the root node, which has to be hooked up properly to the rest of the tree, right? So, yeah, no need to return like a serialized object of any sort. We just return the root at the very top, and it'll check for us if everything else is hooked up properly. Sweet. Okay, we'll call it there, folks, and I'll see you online tomorrow. Have a good night.